We'll get started. So your first problem set is due, and you can either email it to Alejandro. His email address is on the website. If you have a digital version or if you have a piece of paper, you can put it in this physical mailbox. Right? So it's due today, 5 p.m. And the second problem set will be posted on the web soon, and we'll have our usual problem session tomorrow. All right? Very good. All right, so last time we got started, we just were talking, we were giving our introduction to electrostatics and sort of define the field equations, okay? So we have Gauss's law, which tells us about the flux of the electric field through a closed surface, which is given related to the charge enclosed, and the factor 4 pi is representing 4 pi steradians. That's why it's there. And we can think about this as an integral form of Gauss's law. The differential form tells us that locally, the amount at which the field is diverging or converging on a point is proportional to whatever the local charge density is at that point. So if the charge density is 0 at that point, then there's no convergence or divergence from that point. But if the charge density is non-zero, then the L value is 0. Similarly, we have an integral form in terms of the circulation integral, the integral of the electric field around the closed curve oriented in some way. For electrostatics, that's 0. And that means that in electrostatics, the local way in which the field is curling around any point is 0. And these two equations define electrostatics. If we know the divergence and the curl of any vector field everywhere in space, then we know what the field is. In principle, we can integrate these equations to get what the field is, okay? And importantly, when we have this equation that tells us that the field is conservative, and we'll talk maybe a little bit about that today or maybe next week, and can be expressed as the gradient of a scalar field. This is an if and only if thing. If a vector field has 0 curl everywhere, then it can be expressed in terms of the gradient of a scalar, and it's obvious the other way. If it's this, if I take the curl of that, that's 0, because the curl of the curl is like del cross del, and that's like the cross product of a vector with itself, which is 0. And so this is what we call the electrostatic potential, and it can be expressed in terms of the electric field, in terms of this line integral, starting from some point that we have defined to be 0, that's to say at ground, the potential is 0. We can choose that point or some surface of points that are on an equipotential to be ground. And we integrate from any point on ground up to the point of interest, and that gives us what the potential is, okay? So again, from this expression, what we see is that the electric field is perpendicular to the surfaces on which the potential is constant. The equipotential surfaces, the contour map, I'm thinking about, climbing a mountain. I have my topo map, my force, which I would roll down, are perpendicular to those equipotential. If it was a gravitational field, we'd have the same thing, right? The direction of the gravitational field is perpendicular to the directions of equipotential. Okay, of course it goes in the minus direction. If you're at the top of the mountain, the force will take you down. The same thing is true here. Higher potential means that the electric field goes in the negative direction. Okay, right? And the negative sign is there because of its relation to potential energy. as we'll see in a moment, in the same way that we think about potential energy for mechanics. Okay? Very good. All right, so the way that, sort of most sort of generic formal solution to the equations, the field equations, is to integrate them using the potential. So together, the two equations here tell us that del dot minus grad phi, which is minus del dot del phi, is 4 pi rho, tells us that this is true, and this equation we called Poisson's equation, and it combines the two field equations, and thus the solution to this is the solution to electrostatics. We get the electric field by taking the gradient, minus the gradient. So if we can solve this equation, we've solved everything. Of course, I should mention importantly, there's the question of boundary conditions. So this is the situation where we assume that we know rho of x everywhere in space, and it's in some sense localized to some region of space, and there's no charges at infinity. That's the physical situation. We don't got charges at infinity. Infinity is a figment of our imagination. But so this solution we would take typically when we're solving Poisson's equation, we need to think about the boundary conditions and the sort of fundamental case where we're not setting other alternative boundary conditions, which we'll talk about a little bit either today or Tuesday next week, is we take the situation where we take the boundary condition is that the potential goes to 0 at infinity. Okay? So this is the situation where we have localized charges in some bounded region of space.
Is this related to the idea of ground?
Yeah, I mean it is. I mean we're taking ground at infinity here, by definition. Okay? We won't always do that, but to start, we'll go there. Okay? And so the way we solve this, and we're now going to show the formal solution, is we can use the method of Green's function. This is a little bit of a particular part of the more general Green's theorem, which we'll come to next week. But let me just remind you what we said, and then let's find the solution. So the Green's function g, which is a function of x and x prime, and in fact it only depends upon the difference between x and x prime, is the solution to, I don't know what that word is, function, to the Poisson equation for a unit point charge at x prime. So the problem that we want to solve is we want to know what the potential is at some point x, given the fact that there is a point charge with q equals 1 at x prime. Okay? So if we can solve that problem, then we've solved it all by this principle of superposition, because any charge distribution is the superposition of point charges at each x prime. This is the amount of charge in a differential near x prime, and this is the charge density of that point. And so if we can solve this problem for one point charge, we've solved it for all of them, okay? Because what this says is that the potential, so let's put this all together. The Green's function is a solution to the Poisson equation for a point charge, which says then that this is a solution where the charge density is that. Okay? If I have a point charge at position x prime, its charge density is a 3D delta function, which is 0 everywhere except at x prime, in which case it's infinity weight, okay? And so that then is equal to, by definition then, we're looking for the solution to this equation. All right? And by the principle of superposition then, what this tells us is that if we can find the Green's function for a point charge, we can know it for any other charge distribution because we just weight this by the solution here. So this then is equal to right? Because if I look at let's see, I'm gonna have to think about my 4 pi's for a moment. So if I look at del squared phi, that's equal to del squared this. The del is only acting on the unprimed variables. And this is equal to minus 4 pi that, which is equal to minus 4 pi rho. All right, that works. So it's the right solution. Okay, good. All right, so, yes?
Is it always the case that the Green's function will just be a function of the difference between our two locations?
Yes. In all of these problems, the answer is yes, because of the linearity, and we can just displace in the origin. All right, so now the question is, how do I solve this equation? And the way we could solve it is by using the Fourier transform. What? Okay, so the nice thing about the Fourier transform is that it turns a differential equation into an algebraic equation because derivatives become multiplication, okay? Let's remind ourselves how that happens. So let me define, this doesn't really matter what x prime means here, as we just said, this is also true. So let's just solve this problem, and then we can just displace by x prime in the a. Okay, so we'll look at this problem. Let us define the Fourier transform. So I'll call g tilde of k as the integral over k e to the function e to the minus I k dot x. So this is the Fourier transform of the Green's function. in K-space, sometimes known as reciprocal space, okay? This is a three-dimensional Fourier transform, dx, dkx, dky, dkz, and so we have the product of the three integrals for each, these guys. Yeah,
Do we not have like a pi prefactor out front?
good question. The answer is, if I did it this way, then the inverse has to have all the pi's. So, very nice observation. So if I define that, it doesn't really matter. This is a convention where we're going to put the pi's. Sometimes we split up. The two pi's have to go somewhere. But let me just, this is dx. Thank goodness. So now, that makes sense. This is the inverse Fourier transform with the plus sign.
Which is inverse to the Fourier transform.
Yes. So you're correct, Benny. I could have done this and put the two pi's here. This is another way. Often we like to do that, but it doesn't really matter. I have to have the two pi's somewhere because we remember the following thing. If I integrate what is this? It's a delta function, but it's got a 2 pi. This is equal to 2 pi delta of k. And vice versa, I've integrated over k. I get a 2 pi delta of x. Right? Yes?
For the Fourier transform, we have d3 cubed of x hat. Do we keep on the left side of the board?
Oh yeah, the fact that there's an arrow there, I'm sloppy.
Okay.
It's the same thing, just reminding you this, yeah. That notation is, take it or leave it. You know, it sort of depends, if you read the Torah, if there's accents on there or not, they're sort of understood or not. But anyway, that's another story. All right, so with this said, I can look at take this and let me substitute in the inverse Fourier transform for each of these guys, okay? So, the Laplacian acting on the Green's function, well, let's just say it for, take x prime to be 0 since it doesn't matter, is the Laplacian acting on this expression and I need to like the Laplacian of that. Okay? Everyone clear what I just did? I just substituted in g of x, and I took its Laplacian. Laplacian acts only on things that are a function of x, because this is a derivative with respect to x.
Oh, no, these are two different.
Oh, sorry, I screwed up. I brought it inside and then I forgot that I did that. Yes. And my mind doesn't see what I'm thinking. There's like some disconnect going on. Anyway, all right, so how do you do this? Let me ask you a simpler question. What is the partial of x I times k times that? So the derivative gets replaced by multiplication by ik. How lovely, a derivative turned into a multiplication. More generally, suppose I had the gradient of that. This is a scalar function, this is a vector differential operator. What is this equal to? This is ik vector times that. We can do that in many ways. We can use our favorite Einstein summation convention and look at the part with respect to x sub I and bring it down. We get this. Okay? So importantly, when acting on a plane wave like exponential, the del operator gets replaced by I vector k. And so now what do you think this is?
Negative I vector.
Yeah, so this is I dot ik dotted into ik acting on this, which is minus the magnitude of k squared. Okay? So we have that the Laplacian acting on the Green's function can be expressed in reciprocal space as minus k squared g of k e to I k dot x. Okay? Moreover, this is equal to this, which is equal to minus 4 pi times the delta function in 3D. But the delta function in 3D is equal to the integral there are 3 factors of 2 pi, that's why I divided it by that. Yeah.
Is there a tilde over that G or is that?
Yeah, it's a tilde over that G. That one matters. Right? So the Fourier transform of the delta function is 1. Okay? So now, because this is true, I can do the inverse Fourier transform. And what that tells us is that minus k squared times the Fourier transform of the Green's function is equal to minus 4 pi period. Okay? And thus, what we have is that the Fourier transform of the Green's function is equal to 4 pi over k squared, where k squared is k dot k. So we've solved for the Green's function in reciprocal space, and so now what we have to do is take the inverse to get back to configuration space. So we need to now say what is g of x, which is, according to our convention here, the integral over k 2 pi cubed g tilde of k e to the I k dot x. So substituting that in, I get 4 pi over 2 pi cubed times d cubed k e to the I k dot x over the magnitude of k squared. Okay? So, I need to do this integral. Now, how am I going to do that integral? So there's lots of different ways. If I look at this, the integral here, this is a 3D integral in k space. So I'm integrating over this 3-dimensional space with components kx, ky, and kz. But the integrand here only depends on the magnitude of k. So it makes sense for me to think about this in spherical coordinates in K space. Okay? So there is the vector K. The vector K has some polar angle theta sub K and some phi sub K, which is the spherical coordinates thereof. Yeah?
See why the denominator only depends on the magnitude. Why does the numerator?
It doesn't, but it's because the denominator does, as we'll see, it's easier to do this integral. Otherwise, because there's also the angles, but it's just, there's at least this thing, so let's try it, okay? So, what that means then is that this is, in this integral, is k squared dk sine theta sub k d theta sub k d phi sub k. That's, as we remember, the element of volume in spherical coordinates. But the spherical coordinates are relative to the k direction. Okay? Cool. So, the question is, what is the z-axis for a k? We might as well choose that to be the direction of x. So that means I'm going to write k dot x. I'll call this direction, because I can choose anything I want to be the direction that I'm going to call kz. I'll call it whatever the direction of x is. So this then is equal to the magnitude of k times the magnitude of x times the cosine of the angle between them. Okay? So now, voila, I see I've written it in spherical coordinates. It's not just dependent on the magnitude, it also depends on the angle, but in a simple way that I can do the integral. So this integral then, so firstly, this only depends on the theta, and it's azimuthally symmetric. This k dot x is independent of the phi angle. I can swing that around as a cone, you see, and it doesn't matter. So I'm going to do the integral over phi and call this 2 pi k squared dk sine theta. Because when I integrate over all phi, that is 2 pi. I did the integral over phi. Okay? And so this then equals 8 pi squared, and that's 8 pi cubed, so I get a 1 over pi. I get a, look, the k squareds cancel. How lovely. And I get a dk sine the theta e to the I k magnitude of x cosine theta. Okay, and this goes from, k goes from 0 to infinity. That's the magnitude of the k vector. Yes?
Sorry, up there, how did you get rid of k squared g?
I just divided. What are you talking about? I divided by k squared.
No, the line above that, where you got it out of the integrand.
Oh, I took the inverse Fourier transform. I mean, if that's true, then the Fourier transform of that equals the Fourier transform of that.
Okay.
I could, if I wanted to be pedantic about it, I'd multiply by e to the minus I k dot x and do the integral out. But if I have then that means that f equals g.
Okay. Yeah, sorry.
Because I could take the inverse. Yeah. I skipped that step.
Okay.
Okay, leave it alone. Don't be a big professor. All right. What are we doing? We're back where we were here. So what we have is this incredible integral that g of x is 1 over pi, the integral from 0 to infinity dk. And now I'm gonna play a trick on you. Remember, theta here goes from 0 to pi. That's the polar angle, starts at the z-axis, goes all the way down to the south pole. Let me explain how this magic happens.
So we're doing a double integral because it's a density of the electric field?
We're actually doing a triple integral. We're integrating over 3 variables. I did the first integral already. So the integral goes over the magnitude of k, the polar angle theta, and the polar angle phi. This was a 3-dimensional integral because we're looking at a function as a function of 3 dimensions in space, x, y, and z, and we did the Fourier transform, which took us to kx, ky, and kz. But I said, you know what? Instead of kx, ky, kz, I'm going to think of the magnitude of k and theta and phi, because that's the natural symmetry of the problem. And I did one of the integrals over phi because the thing didn't depend on phi, and I could just integrate over phi, and it gave me a 2 pi. Now I have to do an integral over theta and the magnitude. However, I'm going to define, and you always do this, mu as the cosine of the angle. This is a trick that everyone should know for dealing with these kinds of integrals. Why is this a good choice made? Well, it was clearly a good choice made because it depended on cosine, but it's often the case. And look, what's more? What's the differential of mu? Yep, or minus sine theta d theta. So this is actually d mu with a minus sign. Okay? The minus sign says the following, because when sine theta at pi is minus 1, and sine theta of 0 is plus 1. And so, because of the minus sign, I can flip it and go from minus 1 to plus 1. Hey, that's nice. All right. Who would know to do this? Nobody, except when you've done it a million times, because you see the color of my beard, I'm a million years old. I've done it so many times that I know this, okay? But now you do too. And you'll do it a few, 990,000 million, whatever, years on the wall. All right, so let's see how we now solve this thing. Well, that's an integral we can do, right? Because I'll just rewrite it in a slightly different way. I'll put the mu here and the magnitude there, and then I could just, actually, why did I do that? Leave it the way it was, Deutsch. This is just some coefficient, the exponential, so that tells me g of k is 1 over pi, 0 to infinity, dk, e to the ik magnitude of x mu k over I k x going from minus 1 to 1. Right? That's that integral. So when you take its derivative, you get that. That's how you do an integral.
Whoa, no way.
And this is equal to what? It's that minus that, and that's sine. So this is twice the sine of k magnitude of x over k magnitude x. If I multiply top and bottom by 2, I get e to the I blah minus e to the minus y over 2i, which is the sine. Okay? So this then is equal to 2 over pi, the integral from 0 to infinity dk sine of k, how am I going to do that integral? I make the substitution to get rid of the magnitude of the thing, and so this becomes 2 over pi, the integral, oh, sorry, not from 0 to infinity. Yeah, this is 0 to infinity. 0 to infinity, dc sine c, I love saying c, equals kx, and this did the substitution to get rid of the 1 over x. Okay? And then I can do this integral by some hook or some crook, and the answer is pi over 2. Which cancels that. And voila! I get the solution that the Green's function is what we just wrote down from Coulomb's law from the beginning, which says that the Green's function, which is the potential of a point charge, is just 1 over the magnitude of the distance from the point charge to the point of observation. And thus, the Laplacian acting on this is minus 4 pi delta with ground at infinity. Yes?
So earlier we set x bar to be the difference between the two locations, or x hat. Okay.
That's right. I just said, said x prime to be 0 because it didn't affect the equation at all. And then I can just substitute it in. So, complicated thing, one we have to learn how to do, but it's a general solution that we will use again in terms of how we find the Green's function for not just electrostatics, but for electrodynamics. When we start talking about radiation, we're going to have to do the same problem, where we have to think about what are the potentials and then solve for the Green's function associated with radiating charges. It's going to be the same procedure. So lock it in your mind for post-spring break when we're going to come back to the solution again. Okay? Yes?
Same procedure being Fourier transform, fiddle with it, and Fourier.
Yeah, exactly. Take the Fourier transform, solve the differential equation in reciprocal space. If we solve it in reciprocal space, then all that happened there is that we were able to turn a differential equation into an algebraic equation. We can solve that algebraic equation and then inverse Fourier transform to get it in the direct space. That's the procedure.
So reciprocal space, that's whenever you're multiplying instead of taking one.
Yeah, well, reciprocal space means k-space.
Okay.
In reciprocal space, the differential equation becomes an algebraic equation.
Oh,
And so we can solve that algebraically and then take the inverse to get the solution.
Would doing the Laplace transform just be unnecessary extra steps?
It's the same thing. The Laplace transform is typically used when we have some boundary conditions. But here we didn't have to bother. But it's the same idea. All right, let's continue. So what we have established, we have in some sense, in principle, the solution to any problem we want if we know the charge distribution everywhere in space, and it's fixed. We can find the potential by just convolving the charge distribution with the Green's function, and that's the solution. But that's often not the easiest route to solve the problem. It's the most general solution, but sometimes we can solve the problem much more simply than that. And in ways that you know, or at least you knew at one time when you took E&M as a first year or something like that, right? And so, if there is symmetry, we often can solve the problem more simply. Okay? Yeah.
Problem being finding the Green's function.
Find the electric field or the potential. That's what we want to do when we say solve the problem, solve electrostatics. Okay? So, and the key is Gauss's law. So Gauss's law is the killer app. When highly symmetric. And what do we mean by that? So if by symmetry considerations alone, it is the case that I can choose some surface. This is a scripty S is my surface. Such that this is true. Okay, if by symmetry alone we can we can argue that that is true, then it tells us that n dot this on the surface times the surface area. I mean, I can take it outside the integral, and this is the surface area is equal to 4 pi the charge enclosed. And so this tells us what the electric field is on every point on the surface, because we just divide by the area. And that gives us, right? Which also tells us that the units of the electric field is charge per unit area, which we knew already, because it's charge over distance squared in God's units. Today, I'm playing with the robot. Okay? So, these are problems I'm sure you solved in your freshman physics and elsewhere, but we're just going to remind us of them because it's good to be reminded, so you have done it a million times yourself. So, there are 3 basic problems for which we use Gauss's law. There is spherical symmetry, linear symmetry, and planar symmetry. Okay, let's remind ourselves of each of these. So let's start here. Let's say that the charge density only depends on the magnitude of the distance from the origin, and not at all on the angle, right? So I have some spherical symmetry, some ball of charge of some kind. It doesn't have to, it could extend out to infinity in such a way that the charge density only depends on the magnitude of the distance from the origin. It doesn't depend at all at the direction of this, right? So you can have a solid ball of charge where the the charge density is azimuthally and polarly symmetric. Okay? Based on that, we know the following things. The electric field cannot depend on an angle. It can only depend on R. Because how could it possibly know whether I'm at the North Pole or the South Pole? There's no marking on this. If nature doesn't tell us where the North Pole or the South Pole is, there's nothing that distinguishes it. And so if the system has no orientation, the electric field can't depend on the orientation, okay? Moreover, we know that the electric field points away from the charge distribution, and thus it has to point in the radial direction. There's no other way it can point, because how would it know to tilt one way or the other? There's nothing to tell it that I should tilt to the up or down. It has to go away. So we know that this also has to be in the radial direction. So there it is. That's the whole argument you have to use when you're using Gauss's law. The first thing is to use symmetry to argue about how the field varies as a function position and in what direction it must point in. Okay? So given this fact, just from symmetry, we know that we can write down a Gaussian surface upon which this is true. So I can choose any, see, this is like a whiteboard, I have color. I could use, if I choose a spherical surface, then on this surface, dA is equal to E sub R dA. That's to say, the normal to the surface is in the radial direction. And thus, this is true. And this is the same on every point in the surface.
As long as the surface is a sphere?
For the surface is a sphere at the origin. Okay? Which has the same. So with that said, what this tells us is that the electric field, all we need to know to solve the problem, which is to solve the electric field, is we need to know what the magnitude. We know what direction it's in. It's in the radial direction. We need to know what its magnitude is. And this tells us that E sub R is equal to, times the surface area, is equal to the charge enclosed at that radius, times 4 pi. And so this tells us that the electric field as a function of R is whatever the charge 4 pi R squared is the surface area. God, what's wrong with me? That's the area of the surface. So if I have spherically symmetric charge distribution, then what this tells us is that the electric field as a function of position is equal to the charge enclosed as a function of the magnitude of the position over this square. Right? That's the charge enclosed at that radius in that radius larger direction. So it's as if, when we have spherical symmetry, if I had a point charge at the origin, with the same charge as is inside this bubble, the electric field outside that is exactly the same. The electric field on this surface is as if all the charge in that sphere were concentrated at the origin, because that's Coulomb's law. It's the same thing, okay? So let's just take a simple example. Let's say I have a sphere of charge with charge Q uniformly distributed in a ball of radius capital R. So there's this whole ball has a total charge Q and it's uniformly distributed, okay? So what is the charge density of this distribution? It's constant. And what is it? It's the charge over the volume for R less than R and 0 for R greater than R. Okay? So that's the charge density, the charge per unit volume, and it's the same everywhere inside the sphere. Okay? And it only depends on R. It doesn't depend on theta or phi, so it satisfies our condition. Okay? So what is the electric field everywhere in space? Well, it's this. So all we need to know is how much charge is enclosed as a function of the radius of a sphere. So the charge enclosed as a function of the radius is the charge density times the volume of the sphere at that radius, which is equal to Q times R over R cubed for R less than R, and for R greater than R, it's Q. All of the charge is enclosed once the radius is bigger than this. So, with that said, we can divide this by R squared to get the electric field. And so what this tells me is that the electric field as a function of radius, dividing this by R squared, is equal to QR over R cubed when R is less than or equal to R, and it's equal to Q over R squared when R is greater than or equal to R. And so if I were to plot this as a function of distance from the origin, what I find is that I get a linear increase, and then it falls off like 1 over R squared. And at the radius, it's this. Right? Problem you probably solved long ago. But it's good to remind yourself of that. Okay? Quick question. Let's solve a very similar problem, which is, let's say I have a sphere, but I have surface charge. That is charge per unit area, which we typically call sigma, which is equal to Q over 4 pi R squared. Okay, so I take my charge, I will spray it on with my spray paint of charge uniformly, so that everywhere on the surface of the charge of the sphere I have this amount of charge per unit area. Okay. what is the electric field, and there's zero charge inside. It's only on the surface of the sphere, nowhere else. Concentrated on the surface. What is the electric field in this case as a function of position? It's zero inside. So the electric field in this case is zero for r less than r. And what is it if I'm outside?
It's like that with one charge.
So it's as if it were a point charge at the origin, which is, as was said, q of r squared. So in this case, I would have something that looked like this. Right? Notice there is a discontinuity in the electric field. And we'll come back to that. That's a feature. When you have surface charge density, if you have charge that is concentrated on a surface, the electric field will be discontinuous. That's never physically true. It's a mathematical idealization. We love those as physicists because they get us some intuition. I mean, obviously the thing will maybe very rapidly change, and for all intents and purposes, we call that a discontinuity, and that helps us to solve problems through that mathematical idealization.
That's like saying if you go underground, there's like no gravity, it just disappears.
That would be nice. I'm escaping gravity. No, I can't say that, sorry. Yes?
So what happens in reality? Like if I have a surface charge?
Well, there'll be some surface charge density that, and what we will see, and you'll see this in your homework, you might see something that looks like this, where there's a finite slope. Let's say I had charge that was concentrated on a shell of finite thickness. Then inside the shell, the electric field will rise linearly in the same way that we saw here. And then get to the point. And as that shell shrinks, but we keep the total amount of charge fixed, then this becomes an infinite slope. But in reality, it's just a very fast rising slope. Very good. Yes?
Was there some sort of important information encoded in the difference of the 2 points in the?
It is, and it tells us what the charge density itself is. So we'll get back to that in a moment. So what the discontinuity is a measure of how much charge density there is at the surface. In fact, we see that exactly over here, right? Because this point is q over r squared. This is equal to 4 pi times the charge density. So that discontinuity is always 4 pi times sigma. Nice. Okay, let's look at another example. Suppose I have a line charge. So instead of having something on the surface, I have a certain amount of charge per unit length, which we typically call lambda, not to be confused with the wavelength, but in electrostatics we always call it lambda. Okay? So there's a certain, and it's uniformly on this line. So that's, say, if I integrate, if I take a certain length of this guy here, then the charge in that length is lambda times L. That tells me how much charge is in that line. Okay? All right. So, firstly, what do we know? If I have that kind of thing where this is an infinite line, infinitely long, then that tells me something about the symmetry, right? There's only this one coordinate, and I can't tell where I am on this coordinate, right? Moreover, so what coordinate system should I think about when looking at a problem like this? Cylindrical coordinates, because cylindrical coordinates tell me that there's a z-axis and there's a azimuthal angle around the z-axis, and there's some distance from the z-axis. Now, what letter should we use for that? God, there's no good choice. R. R is our star coordinate. Rho is our charge density. So I'm going to use S. Okay, that's the distance from the axis according to cylindrical coordinates. Can the electric field? Can the magnitude of the electric field depend on Z? No. Where am I? I don't know. Where's the beginning? There is no beginning. There is no end. I don't know where the origin is. There's no way to know where I am along Z. And if there's no marker in the world that tells us where Z equals 0 is, the thing cannot depend on Z. Moreover, can it depend on phi? No. I mean, where am I in phi? There's no azimuthal dependence of this. So the only thing it can depend on is S. So the electric field, we know, can only depend on this cylindrical distance S from the origin, and it can't depend on Z or phi. What direction must it point in? Radially outward. It has to, because how would it know to tilt one way or the other? There's nothing that tells us to do it. So this is in the radial out the S direction. So with that said, what Gaussian surface should I choose such that E dot dn, or E dot the normal, is the same no matter where I am on the surface? There are two things in using Gauss's law. Is first, write down the form based on symmetry, step one. Step two, choose a Gaussian surface such that E dot the normal is constant. So what surface should I choose? A cylinder, because if I choose a cylinder, this is the z-axis, then the normal is in to the surface, the label of the soup can is in the radial direction, no matter where I am. Okay? So with that said, choosing my cylindrical surface, then n hat dA dotted into the electric field is equal to dA times the electric field at that radius. And so if I do the integral over the surface, which includes the top and bottom of the soup can, not just the label, firstly, the electric field dotted into this is in the z direction, so that's 0. So it doesn't contribute. The only thing that contributes to the flux is the things around the label of the soup can. So this is equal to, and what is the surface area of this label of the soup can? It's the perimeter times the length. 2 pi s times the length of the soup can. Times E sub s is equal to the charge enclosed as a function of s. Okay, times 4 pi. And so what I find is that for a line charge, the electric field falls off with the radial distance from the axis of the line 2 times the lambda so the charge enclosed as a function of s per unit length. And in this case, over s. So this was for a line charge. I could solve a similar problem, which is, let's say I have a rod of charge that's infinitely long, which has a charge per unit length distributed within it. I would do the same problem like I did here for the sphere, where I would take the charge, distribute and look at the charge density in the cylinder, and I would see the same kind of rise. Okay? Won't do those details again, you can review them for yourself. Let me quickly say a couple of words about planar symmetry. So let's say I had oh God, am I the worst? Plane, if there's a plane, it's an infinite plane. And say, it could be the XY plane, okay? And I spray on it surface charge that is uniform on the plane. And I have sigma is the surface charge density. Okay? So it doesn't depend if this is the XY plane, the surface charge is independent of where I am in X and where I am in Y. The amount of charge only depends where I am on Z. And it's zero everywhere except at Z equals 0. Okay? So this is, say, the XY plane. I could formally write the charge density as sigma delta of Z, because this is the density of that along Z. This is the charge per unit area. This has the units because the delta function has the units of 1 over length. This has charge per unit area, charge per unit volume. Okay? So my charge distribution only depends on the Z. It doesn't depend on where I am, which tells me that the electric field as a function of position can only depend on Z, because where am I relative to X and Y? There's nothing in nature that marks X equals 0 or Y equals 0. Everything is the same no matter where I am, because this goes on to infinity. So my electric field only can depend on Z. Moreover, it must be in the Z direction, because how would it know to bend this way or that? There's nothing that tells us. So we know the electric field only depends on the Z axis and points in the Z direction. So what we do in this case is make what's back in the 19th century was called the Gaussian pillbox, because I guess they have these kind of boxes. Well, this is supposed to be below the axis, and you can't see it. That's why it's dotted. Such that it's like my soup can, but now the radial part has no dot product, and only the end caps have this. And if this has a little area A, then if I do this over my Gaussian pillbox, I get only a contribution from the end caps. And they add, right? So this tells me that the electric field Z so here I'm at Z and here I'm at minus Z. I'm symmetrically about this. But they point in the opposite direction. Okay, so I guess I should say one other point here. It must be the case that Z, the magnitude here must be the same. Why is that?
Because the charge distribution doesn't look this way or that way.
Yeah, I can't tell what's above the plane and what's below the plane. It doesn't have, there's nothing that tells me it's pointing in one direction or the other, right? So, because of that, this tells me that, since it points away, what this says is that this is equal to 2 times the area, the electric field at Z, is equal to the charge enclosed, and the charge enclosed is the area times the charge density, times 4 pi. Which tells me that the electric field, as a function of Z, is equal to 2 pi sigma. Constant. So what this says is that here's the plane. I'm looking now on the XY plane. Here's my charge density. Which is on the surface. My electric field points in the Z direction. And it's the same. Everywhere. Except above and below. It always points away from the plane, so it flips. Like that, yep.
If this was like if you weren't looking at the bottom of the plane and you were just concerned about the top and say like it's just infinitely solid below and
Yeah.
there's no field.
Yeah.
Would it still be constant?
No, it
That's what
wouldn't.
I thought.
It wouldn't. So we're gonna solve the following problem, you will in your homework. Let's say I have a slab of charge. Okay? So, you know, it was a solid slab. The electric field would change within this. In this problem, if I look at the electric field along the z-axis as a function of z, above it is 2 pi sigma. Below it, if I've chosen to choose some direction of orientation like this, okay? Notice that the electric field is discontinuous. As we said, when I have a charge that's concentrated on a surface, then there is a discontinuity in the magnitude of the normal component, the component perpendicular to the surface, and that discontinuity is always 4 pi over the charge density. Now, if we had something like this, what we would see is something that went more like that for this problem. And as I compress this, this curve would get more and more rapid, and I'd have a bigger and bigger right? Yeah, kind of question, yeah.
Shouldn't there be a negative sign in the symmetry argument? Like AZ equals negative B of negative Z?
Yeah, you're right. It should, the if I call this Z direction, you are absolutely right. The Z component of this is minus that. You're absolutely correct.
And then how do you fix the?
No, because in this case, n hat here is easy, and in this case, it's minus easy.
Oh, I see.
Yeah, but you're absolutely correct, Eric. It's gotta be minus by the symmetry argument, and the dot products add.
Or the function of U and C, or wait, no.
What is your question?
Wait, no, I got
So if we call the Z, if we break the symmetry and call this direction the Z direction, then above the plane, it points in the positive Z direction. Below the plane, it points in the minus Z direction. And those contribute equally to the top and bottom of the soup. And they add up together to be twice that. Very good. All right, we'll call it quits for now. And we'll continue in our problem session tomorrow. All right, see you then.
Thanks for playing.